How did the universe's elements form? The origin of the elements commences during the initial phases of the Big Bang, when the universe was merely a few seconds to a few minutes into its existence. The origin and evolution of the elements in the universe is a remarkable tale that begins with the very inception of our cosmos. The question of where all these elements came from leads us back to the earliest moments of the Big Bang, when the universe was but a few seconds to a few minutes old. At that moment, the entire universe was confined to a space millions of times smaller than it is today. The incredible densities and energies within this tiny volume created conditions in which nuclear reactions could occur. In fact, the temperatures were so extraordinarily high, exceeding 1 billion degrees, that even protons and neutrons couldn't exist as stable entities. Instead, the universe was a seething primordial soup of more fundamental particles known as quarks and gluons. However, the universe was in a state of rapid expansion, which meant it was also cooling down. As it cooled, the quarks began to bind together, forming the first protons and neutrons without being instantly annihilated. Protons, being slightly lighter than neutrons, had a slight advantage in this early phase of particle production. As the universe reached a few minutes of age, it had cooled to a point where it could no longer create new protons and neutrons. This meant that the first heavy particles, protons, and neutrons were the only ones that the universe would produce in significant quantities, excluding rare high-energy interactions in the future. At this stage, the universe contained roughly 6 protons for every neutron. Neutrons are inherently unstable and decay with a half-life of around 880 seconds. Some of the neutrons immediately began to decay, while others began binding with protons to create the first atomic nuclei. Among these early elements, helium-4 was particularly significant. Helium-4 consists of 2 protons and 2 neutrons, and possesses the highest binding energy of all light elements, making it the easiest to form and the most challenging to break apart. As a result, the vast majority of these neutrons were incorporated into the production of helium-4. Cosmologists, through calculations and observations, have determined that the universe's initial composition comprised approximately 75% hydrogen, which is essentially a single proton, 25% helium, and a trace amount of lithium. These proportions are precisely what astronomers have observed in the composition of the universe. This early nucleosynthesis process, which occurred within the first few minutes of the Big Bang, laid the foundation for the elemental composition of the cosmos as we know it today. The remarkable journey of these fundamental building blocks, from the seething quark-gluon plasma of the early universe to the formation of the first atomic nuclei, is a testament to the interplay between the extreme conditions of the early universe and the fundamental physical processes that govern the cosmos. It is this intricate dance that has given rise to the rich diversity of elements, from light gases like hydrogen and helium to heavy metals like lead, that make up the universe we observe today. Stellar nucleosynthesis, the next stage in the appearance of the elements in the universe, is an awe-inspiring cosmic saga that unfolds over billions of years. It all begins with the Big Bang, a cataclysmic event that set the stage for the creation of all matter and energy. However, the immediate aftermath of the Big Bang was not a place where elements as we know them could exist. Instead, the universe was a seething, hot, and dense soup of fundamental particles, such as protons, neutrons, and electrons. It wasn't until hundreds of millions of years after the Big Bang that the first generation of stars began to emerge. These stars, powered by the process of nuclear fusion, played a pivotal role in the formation of the elements we find in the universe today. The primary fusion process in these stars involved the conversion of hydrogen nuclei into helium through a series of nuclear reactions. The incredible energy released by this fusion process not only allowed stars to shine brilliantly, but also created a residue of other subatomic particles, such as neutrinos and gamma rays. It is this leftover energy, along with other processes, that eventually led to the formation of elements beyond hydrogen and helium. These newly formed elements would go on to shape the chemical composition of the cosmos. Stars have an abundant supply of hydrogen, which allows them to continue burning for an extraordinarily long time, sometimes for billions or even trillions of years. During this prolonged fusion process, a fraction of the hydrogen is gradually transformed into helium, and over time, helium becomes more prominent in the star's core. As a star nears the end of its life, particularly stars like our Sun, it undergoes a dramatic transformation. At this stage, it starts fusing helium into heavier elements like carbon and oxygen. This shift in fusion reactions is responsible for the creation of carbon and oxygen, which are now abundantly present in the universe. In fact, oxygen is the most common element on Earth, forming a significant part of the planet's crust and atmosphere. The incredible diversity of elements doesn't stop there, especially when it comes to more massive stars. Stars that are at least 8 times the mass of our Sun are cosmic forges of even heavier elements. In the final stages of their existence, these massive stars undergo a series of fusion reactions that culminate in the creation of elements like nitrogen, neon, silicon, sulfur, magnesium, nickel, chromium, and iron. Ultimately, the process of stellar nucleosynthesis is responsible for the rich tapestry of elements that we find in the universe, from the lightest hydrogen and helium to the heavier elements like iron. These elements, created within the fiery crucibles of stars, are then scattered into space when stars explode as supernovae. This dispersal of elements provides the raw materials for the formation of planets, like our own Earth and life as we know it. The story of the elements is a grand cosmic narrative that illustrates the interconnectedness of the universe and our place within it. Aftermath: nucleosynthesis. The creation of elements in stars is an incredible cosmic drama, but it doesn't stop at our. Above this point, on the periodic table, the energy required to fuse elements into heavier ones becomes a significant barrier. In fact, rather than generating energy, the fusion of elements beyond iron consumes more energy than it produces. As a result, these heavier elements are formed only rarely, deep within the cores of the most massive stars. So where do the rest of the elements in the periodic table come from? The answer lies in the remarkable and often cataclysmic deaths of stars. Stars, regardless of their size, eventually meet their end through a variety of fascinating and complex processes. Smaller stars, like our Sun, undergo a more gradual and less violent transformation as they age. They expand into red giants and then shed their outer layers, effectively turning themselves inside out. This process scatters their elemental content across their stellar systems, seeding space with the products of their nuclear fusion. What remains of these smaller stars are white dwarfs, incredibly dense and compact celestial objects made predominantly of carbon and oxygen. On the other hand, massive stars, those many times more massive than our Sun, meet a more dramatic fate. They explode in violent and spectacular events known as supernovas. These explosions release an immense amount of energy and create shockwaves that rip through space, ejecting the elements forged within their cores. The remnants left behind are neutron stars, incredibly dense spheres composed almost entirely of neutrons. But the story doesn't end there. White dwarfs can also contribute to the formation of elements in a unique way. If a white dwarf in a binary star system accretes material from its companion star, it can reach a critical mass and undergo a type of supernova known as a type I supernova. This explosion releases a vast amount of energy and scatters elements into space. Moreover, neutron stars, which are incredibly dense and massive, can merge with each other in dramatic collisions known as kilonovas. These cataclysmic events unleash a colossal amount of energy, and during the violent collision, they produce a wide range of elements. All these stellar deaths and catastrophic events involve copious amounts of radiation, energy, and high-speed particles. This turbulent environment is the perfect setting for the formation of new elements. Its fluid celestial climates allow new elements to open out to formation. These newly formed elements are not confined to the radiant star. They are ejected into space, where they mix with interstellar gas contributing to the cosmic tapestry that shapes the universe we observe today.